Okay, I'm going to call this video proof support video. So I found this worksheet online. I'm guessing it's not from the US, which is kind of fun, but I don't know exactly where it came from. So thanks to whoever put this together. So what they're asking us to do is for each one, they want us to say, well, if A is true, is B sometimes or always true? If it's sometimes true, then give the counterexample that makes it so that it's not always true. And then they want you to turn around and say, if B is true, if B is true, is A sometimes or always true? Once again, the sometimes give a counterexample. So in this one, we said that that both are true, that A implies B and B implies true. So that's always true for both of them. On this one, we know that that this B implies A is true. B implies A. That one's good to go. But the other direction does not work. So if I try A implies B, it's false whenever our counterexample is when x is equal to -5. Okay, because if -5 squared is equal to 25, but -5 is not equal to 5. The next one, the absolute value of x is greater than 3, therefore x has to be greater than 3. If I go this direction, the A implies B, that one is false, and my counterexample, so hang on, we'll do this. My counterexample for the first one, A implies B, would be if x is equal to, well, -5 again. The absolute value of -5 is 5, making this a true statement, but -5 is not greater than 3. Going the other direction, x is greater than 3, then the absolute value of x is greater than 3. And that way, so B implies A is true. Now, if you go back, I've already worked an answer key, and I wrote this a little bit differently, but I'm kind of having fun changing it up. So this one, A implies B equals, A implies B is true. If A equals B, then I can multiply both sides by the same, and it would be fine. The other direction, though, caught people, and that is if C were equal to 0, then I could have 100 times 0 and a trillion times 0, and that would give us 0 equals 0, which does not tell us that 100 equals a trillion, or whatever numbers I want to come up with. So my counterexample is C equals 0. The next one, the x squared has to be less than 9, which tells us that x has to be less than 3. Going this way is fine. This one, I'm going to write off to this. Well, here we go. If I have a number line, -3 and +3, in order for x squared to be less than 9, I need to live in between those two values. So 0 squared is going to be less than 9, but -4 squared gives me 16. Okay, so going this direction, if my x squared is less than 9, then yeah, whatever my x would be less than 3, because it's going to be in this world, which is less than 3. So A implies B is fine, but the other way, if I use something like, I'm having fun with -5. If I were to say x is equal to -5, -5 is less than 3, but -5 squared becomes 25, which is not less than 9. Okay, so there's a counterexample. The next one, this one is actually, it helps. I did this 4 times already 5. I worked it once by myself, and then I worked it with all 4 of my classes, and now I'm cruising through this. So if I'm too fast, sorry. But on this one, just because this is basically telling us y is negative, but if x is also negative, so our counterexample would be x is equal to -617 is my birthday. That makes this no longer a true statement. A negative for y times a negative for x now gives me a positive, which will not be less than 0. Going the other direction, if my x is the negative number and my y is the positive number, then this would not be true. So this is a counterexample for both of them, for both directions. Okay, the next one, A, B, and C are consecutive numbers. A, B, C is a multiple of 3. Okay, so what happens, and this is one I would sit in class and I'd hold up my fingers and we'd kind of go from there. So if I have 3 consecutive numbers, then then one of these 3 has to be a multiple of 3. Let's think about it again. If I'm dividing by 3, either I'm going to get it perfectly divisible, so it has a remainder of 0, or it has a remainder of 1, or it has a remainder of 2. Okay, and so, but then that cycle repeats itself. So if I have 3 numbers in a row, of these 3, the only thing that can happen is it could be a remainder of 1, a remainder of 2, and a remainder of 0. So one of these 3 must be must be a multiple of 3. Therefore, the whole thing is a multiple of 3. So the A implies B is true. ABC is a multiple of 3. That tells us this going this direction. Well, no. What if A was equal to 3 and B was equal to 17 and C was equal to, I don't care, 11? Pick numbers. It really doesn't matter. This is a multiple of 3 because there's the 3 that's multiplying through, but those numbers are not consecutive. Okay, P is a prime number greater than 3. Okay, so then this one, if P is a prime number greater than 3, then P is one more or one less than a multiple of 6. Okay, so if it's a prime number greater than 3, that means it has to be odd. Okay, and so then that number is either going to be one more or one less than a multiple of 6. So this is one where using my fingers really helped. So if I've got a prime number, so here's my prime number P. This looks funny in the video. It made more sense in class. Let me try and write something out. Okay, if I have a prime, well, so if this is my P, it's going to be odd, which tells us that on either side of it, P minus 1 and then P plus 1, this one is going, they both have to be even. Yep, that's an even. That's an even. Okay, so, right, because we know that if it's a prime number bigger than 3, it's going to have to be odd. Therefore, the ones on either side of it are even. Well, and we know that this one can't be the one that's divisible by 3, because if it were divisible by 3, it wouldn't be prime anymore. So that means that we've got 3 consecutive numbers, and if you notice, 3 consecutive numbers, and one of them has to be a multiple of 3. Okay, so this could have a remainder of 0, 1, and 2. Here's your multiple of 3. Or it could be, this can't have a remainder of 0. So one of these has to be a remainder of 1, and the other one, hang on, let me try that again. This can't have a remainder of 0, so one of those has to. Okay, so this A implies B is true. And then P is one more or one less than a multiple of 6. We used the 2 examples that we saw the most or heard the most. People kept telling me in class 25. Notice that that's one more than 24, which is a multiple of 6, but 25 is not prime. The one I had come up with was 35, which is one less than 36, which is a multiple of 6, but this is not prime either. Okay, that's a pretty clever problem. A, B, and C are consecutive numbers. ABC is a multiple of 6. That kind of comes back to this, where if we've got 3 numbers in a row, either we're going to go even, odd, even, or we're going to go odd, even, odd, but we have to have one or 2 of these 3 will be even. Okay, and the other thing that we said is that if we have 3 consecutive numbers, one of them must be a multiple of 3. So you multiply them all together, you've got a multiple of 2 in there, you've got a multiple of 3 in there, therefore it's a multiple of 6. So A implies B will be true. ABC is a multiple of 6. Okay, well, one of my little darlings said, well, what if A, B, and C are all 6? I'm like, ho, ha, ha, you 6, 6, 6. Okay, whatever. But case in point, A equals 6 and B equals 1 and C equals, I don't care, 3. That multiplied together is a multiple of 6, but they're not consecutive. So there's your counterexample. This one is really clever. Okay, so I'm going to turn the paper over. This is one actually that I think we could say that A implies B and B implies A, but I want to talk about this one. My HL kids have had to prove things like this for a number of years, so we will, when we get to proof by induction, you'll learn how to prove that. But let me make sense of it. Okay, so what this is telling us is that U sub 1 was equal to 1, and U sub n plus 1 is equal to U sub n plus 1. Okay, so my very first term, U sub 1 would be equal to 1. Well, my second term, U sub 2 would be equal to, well, that's 2 is 1 plus 1. So that means that this n value right here is equal to 1. So this is U sub 1 plus 1 plus 1. Well, U sub 1 is 1, so that's 1 plus 1 plus 1. and that's equal to 3. I'm going to move that over. Okay, u sub 3 is equal to u sub 2 plus 1. That means my n value right here is now 2. That my n value is 2. And so my u sub 2, we look back to the previous one, u sub 2 was 3. This is 3 plus 2 plus 1, which is equal to 6. Okay, u sub 4, u sub 3 plus 1 is equal to u sub 3 plus 3. That's my n value plus 1, which is equal to 6 plus 3 plus 1, which is equal to 10. And my students recognized that we were, hang on, I was adding 2, I was adding 3, I was adding 4, and so they thought, okay, the next one should be 15. So they were right, but let's talk about that. U sub 5 would be equal to u sub 4 plus 1, which is u sub 4 plus 1, which is 10 plus 4 plus 1, and sure enough, that's 15, so that was adding 5. So what we notice here is that if these first differences were all the same, it would be linear, but they're not. And what I notice is as I move down this way, the second difference is the same. So this was all the same, which tells us that it's quadratic. And sure enough, if that was u sub n is equal to, I think it's, let's see if I remember correctly. Yes. Okay, so when I plug in, and when I test a term, u sub 5 is equal to 1/2 times 5 times 6. Well, that's 30. Half of that is 15, and sure enough, that's 15. The way that we proved this for HL was by proof by induction, which we will continue to do. So don't worry about that part of things, but I thought this was a pretty nifty little problem. We're going to just keep on going in the same video. And that was the second thing that we did was the back. And basically, this is preparing us to have to prove the sum of two odd numbers is even, okay? So what we're going to do is we're going to say, well, how would I turn this statement into math? How would I turn this into an expression that I could work with? And that is, well, to get an odd number, if I do something like 2m plus 1, where m is an integer, 2 times that will always be even, add 1, and it's always going to be odd. So here's an odd number. Here's another odd number. And I'm going to once again make this an integer. So I'm saying that 2m plus 1 and then plus 2n plus 1. So they don't tell us that those odd numbers are related to each other in any way, so I wouldn't want to use the same variable. Is equal to an even number is equal to 2k. So I could say where these are elements of the integers. Or I might say that it's 2m plus 1 plus 2n plus 1, and I might just write it out, is divisible by 2, and then we'd talk our way through it. Okay, but that's probably what they wanted. The next one, the sum of a positive integer and its square is always even, so we're going to say let n be an element of the positive integers, and then we can say n plus its square, n squared, equals 2k. The sum of 3 consecutive positive integers is a multiple of 3. So let n be an element of the positive integers, so n plus. And this one, then we could say, well, n plus 1 was to be the next consecutive plus n plus 2 is equal to a multiple of k, multiple of 3 would be 3k. Or you could do the same as divisible by 3. Something like that. On this one, we could also, sometimes it's helpful to use n minus 1 and then n plus 1. But on this one, we'd have to say that n would have to be greater than 2, greater than or equal to 2, and an element of the positive integers. Because I couldn't, the smallest value here, sum of 3 consecutive positive integers, I'd need to make sure that was still a positive integer. This is just extra. This part right here answers the question. The product of 3 consecutive positive integers is a multiple of 3. So this is n times n plus 1 times n plus 2 is equal to 3k, would be let n be an element of the positive integers. Okay, whatever. Cool. The perimeter of a square, this one, you would move to formulas at some point, but I would just say if the perimeter of a square equals the same of the circumference, then so this would imply that the circle has greater area of the circle is greater than the area of the square. And we'd need to turn this into different equations and stuff. So the perimeter would be like 4s would be equal to, what, pi r squared. And then this equation is, oh, I lied, circumference. Oh, my goodness. Don't tell it I taught geometry for 7 years in a row. Okay, this is 2 pi r. And you need to manipulate this because the area of a circle is pi r squared, and then the area of a square is side squared. So we're going to have to write one variable in terms of the other and come up with some sort of, well, they didn't ask us for the proof, but there you go. The other thing that came with this was they have these these statements right here that could be part of a proof. So these are the statements of a proof, and then this is a separate proof right here. And I don't want to talk about it right now. So this is, this was what, we did these two sides on the same day, and then I haven't handed this out yet. So I'm likely to do it at some point. It's a cut and paste. Put these in order and go from there. Good luck. Practice, practice, practice.